All right, welcome back, you guys. A little review. We're going to take a look at inverses and see if we can make the connection between a function and its inverse today, and its derivative. Their derivatives. And if you remember inverses, like if I had y equals x squared minus 1 that's listed here, when we found the inverse, you remember how we switched x and y, and then we would solve for the new y? This is how we would find y squared is x plus 1. And square root, so y equals plus or minus square root of x plus 1. So the inverse of x squared minus 1, if I restrict the domain at least, is, I'll just take this, the positive one, is the positive, that's its inverse. There's its inverse, right? You remember doing that in pre-calculus, hopefully. So that's how you find an inverse. In this case, we're given both the function and the inverse. Let's go ahead and take the derivative. And let's go ahead and then take the derivative of the inverse and see if we can't make the connection. All right, so here's our function. If we were to take the derivative, we got this power rule 2x minus 0, right? There's the derivative of the original function. Now let's go ahead and let's look at the inverse here. Here's our inverse, x plus 1 to the 1/2. And if I was to take its inverse, f inverse prime of x, I'd have 1/2 x plus 1. Now it's to the 1/2 minus 1, so negative 1/2 times the derivative of the inside, which is just the 1, right? Chain rule on that. And so this just ends up being 1 over 2 square root of x plus 1. And that's the derivative of the inverse. Well, it may be hard to see, but if you're looking at these and comparing the derivative of the original, derivative of the inverse, well, if you take this 2x, the derivative of the original, and you put it 1 over, so you flip it, so it's the reciprocal, and then you replace that x with the actual inverse of x, so I replace x with the inverse function, right? Square root of x plus 1. That's the derivative of the inverse. And so that's your connection for that. The derivative of the inverse is 1 over the original derivative with the inverse plugged in. Okay. And so let's go ahead and do that, and then we'll evaluate it. And remember with inverses, like if your function, if your original function is f of x is x squared minus 1, let's say you plug 1 in. So you get f of 1 is 0, right? That means if you plug 0 into the inverse, then it would spit out 1, right? The x's and the y's flip-flop. This is the 0.1, 0. So if I plug 0 into the inverse, 0 plus 1 squared of 0 plus 1 is 1, right? They flip-flop, 0 and the x and the y. So we're going to go ahead and find the derivative of the function, derivative of the inverse, and then we're going to plug in the input, and then on the inverse we'll plug in the output of the original input, if that makes sense. All right, here we go. So our first one we've got f prime of x equals 1/2 x plus 7. Now it's to the negative 1/2. Derivative of x plus 7 is just a 1. So we got 1 over 2 square root of x plus 7. And there's our derivative. Okay. Now let's go ahead and do, and we'll go ahead and take that derivative at x equals 2. So f prime, it says find that at x equals 2. Square root of 9 is 3, so I got 2 times 3, I got 6 on the bottom there, so I got 1/6 there. All right. Now let's do the inverse. So the inverse is right here, x squared minus 7. So let's go ahead and find the derivative of the inverse, so 2x. And then this time, we're plugging in you know, the original function was square root of x plus 7, and I plugged in 2 into the derivative, right? I plugged 2 in. So f of 2 is square root of 9, which is 3. F of 2 is 3. So this time when I run the inverse to see this relationship, that it's the reciprocal, instead of plugging in 2, I'm plugging in 3. Plugging in x equals f of 2, which is 3. I'm plugging the output in to the inverse here. Okay. So f inverse of 3 is, and let me actually write that, you know, they're asking us to do it at f of 2. Well, f of 2 is 3. So 2 times 3 is 6. And hopefully you notice that these are inverses of each other, right? 6 and the 1/6. Right, we ended up with 6 here. We ended up with 1/6 up there. All right, so let's go ahead and do this one. And let's take the derivative of the inverse, and let's go ahead and use the fact. So instead of, we don't notice I don't have an inverse given here. So I'm going to use the fact that the derivative of the inverse is 1 over the derivative of f at f inverse. Okay, and so let's go to the side for a minute, and let's just find the derivative of f of x. So here's our f of x. So f prime would be 6x minus 7, right? And so what this becomes is 1 over 6x minus 7. But what's going in right here is f inverse, right? So they're wanting this at, they want the derivative at x being 0, I'm sorry, x being f of 2, which is, you know, if you plug f of 2 into the original, you get 0. So they're saying plug the y in, right? Plug that output in. So we want this to be 0 right there. All right, so we're finding at f of x of 0, which is, oh, I'm sorry, you guys. Good grief. X of 0. I'm plugging 0 in. I'm plugging f of 2. Good grief. 2 in. What is that? I screw that up. F of x is 3x squared minus 7x plus 2. Three times 4, 12, minus 14. Oh, that's right. I'm sorry. Yeah, it is 0. Okay. So f prime at that. And so we got the 6 times 0 minus 7. So we got 1 over 0 minus 7. Negative 7. Negative 1. Negative 7. Oh my gosh. There we go. All right, let's move on. Guys, my apologies. I'm just realized that I messed this up here. When I want at f of 0, you know, f of 0 into the original is 2. I want my input on the inverse then to be 2. Sorry about that. So this is it. X being the 2 for the inverse, right? I want to put that in. So my apologies on that. I screwed that up, but I don't want to go back here. Let me just fix it right here. There we go. Sorry about that. That's what I get for not looking at that a little closer. Okay. All right, let's move on here. Derivative of the natural log. I think it's worth looking at the proof of this. If I let what I'm trying to do, you guys, is prove that the derivative of the natural log of x is 1 over x. So I'm going to start with y equals ln of x. And if I take e to both sides, then I'd have e to the y equals x. And then I go ahead and use my implicit differentiation right here on this. Then I would have ln of e. I'd have e to the y. I'd have derivative of y, because remember, variables don't agree. This is my chain rule. That's my implicit differentiation. And then I'd have the derivative of x over here, which is just 1. And then what I'd do, of course, the natural log of e, this is just 1, right? So I got e to the y dy dx equals 1. So I solve for dy dx by dividing both sides by e to the y. So I got 1 over e to the y. Now remember, I let y be the ln of x. So let me replace that with the ln of x. And so my derivative, e to the ln of x, is just x. Right? So the derivative of the natural log is 1 over x. So we just proved that right there. Right? There it is in chain rule form. That's the same thing. That's 1 over u times whatever the derivative of u is. So let's go ahead and do some of these. So, well, let me do a more simple one first. Let's say we had the natural log of 2x. So its derivative would be 1 over that. But then I'd run chain rule times the derivative of 2x is just 2. So this just ends up being 2 over 2x, which is just 1 over x anyways. In that case. All right, but let's go ahead and do the next one that's actually shown here. So this derivative would be 1 over that times the derivative of that. So I'm taking the derivative of 9x to the negative 2. All right, so that would be negative 18, x now to the negative 3. So y prime ends up being, and I'm going to take this 1 over 9 over x squared is x squared over 9 times negative 18 over x cubed. So I got negative 18 over 9, negative 2 over x. There's the derivative again for that problem right there. So again, the derivative of the natural log of x, 1 over x. But you want to remember, of course, you got chain rule involved, right? Let's do it with this next one, cosecant. And this is just saying, you know, the natural log of the cosecant. Why do they have that cosecant on there? Well, if you remember, the natural log of x looks like this, right? Here's the natural log of x. So its domain is positive. That's why that absolute value is on that cosecant. It's saying cosecant's got to be positive because cosecant does have some negative values, right? So they're saying, hey, let's make it work for the natural log here and make it positive. But let's go ahead and take the derivative. So we got 1 over that cosecant of x times, now we take the derivative of the cosecant. Well, the derivative of the cosecant is negative cosecant cotangent. And so we got negative cosecant x cotangent x all over cosecant of x, which is negative cotangent of x. And that's the derivative of the natural log of the cosecant of x. On this next one, I would go ahead and run the quotient rule here. So the dy dx would be derivative of the top 0. Derivative of 1 is 0 minus derivative of the natural log is 1 over x. Here's the derivative of the top times the bottom minus the top. Derivative of the bottom, derivative of x is 1 all over bottom squared. So I got negative x over x. I got negative 1 minus 1 plus the natural log over x squared. So this derivative is just negative 2 plus the natural log of x all over x squared. Looks like I've got double composite here, if you will, right? So chain rules involved. When I take this derivative, I got natural log of that stuff. So I have 1 over that stuff times, now I take the derivative of the sine of the natural log of theta. Well, the derivative of the sine is the cosine of that stuff. And then I got to take the derivative times derivative of the natural log, right? I'm taking the derivative of the inside now. Derivative of the natural log is 1 over theta. Okay. And so this ends up being the cosine of the natural log of theta over theta times the sine of the natural log of theta. Well, I have cosine natural log over sine natural log, so cosine over sine would give us cotangent. So I got cotangent of the natural log, and I still got this theta at the bottom, right? And that's our dy d theta, or theta y prime. All right, next one, I'm going to go ahead and take this derivative. So derivative of the natural log is 1 over that stuff times. So I got to take the derivative of this stuff inside. Well, I've got to use a quotient rule, it looks like. So derivative of the top times the bottom minus the top. Derivative of the bottom, derivative of x plus 3 is just a 1. 1 plus 0 all over bottom squared, right? And so I got 1 over 2x over x plus 3 is x plus 3 over 2x. And then I've got, let me clean this up, 2x plus 6 minus 2x over x plus 3, 20 squared. 2x's are gone. So I've got 6, I got an x plus 3, I've got a 2x, I got an x plus 3 squared. So one of these x plus 3's cancels, leaves me with 1 down there. 6 over 2 gives me a 3. So it looks like I've got y prime being 3 over x times x plus 3. Here we've got, take this derivative, and I've got 1 over this stuff. Oops. Now I got to run the power rule on this, so times, so it's 1/3 that stuff. So 1/3 minus 1, so minus 2/3 times. Now I got to take the derivative of the inside. So I got to do quotient rule on this. Derivative of the top, derivative of x minus 1 is 1 times the bottom minus the top. Derivative of x plus 1 is just a 1 all over bottom squared. Okay. So I've got 1 over, and notice here I've got x minus 1 over x plus 1 to the 1/3. I've got a 3 here times 3, and I've got this x minus 1 over x plus 1 to the, that was to the negative 2/3, so that goes down and becomes a positive 2/3 down there, right? And so that'll just end up being an x minus 1 over x plus 1 to the 1 there. Let's see, over here we've got x plus 1 minus x plus 1 over x plus 1 squared. Again, 1/3 plus 2/3 is to the 1. Over here I've got x minus x, that's gone. 1 plus 1 is a 2. over x plus 1 squared. And so I've got, let me take this over here. I got x plus 1 over x minus 1, because it's 1 over that, so it'll flip that, right? So I've got and I got a 1/3 out front of this. And I've got this 2 over x plus 1 squared. So it looks like one of those x plus 1s will cancel. That one cancels with one of those, so it leaves me with one left. So it looks like my y prime just ends up being 2 over 3, x minus 1, and then x plus 1. There's my dy dx there. You know, here I'm going to use my log properties. If you remember, the natural log of u to the n is n ln of u. Remember that? That's the power rule of natural log. So these are unique to logarithms. Maybe you remember the natural log of u times v is ln of u plus the ln of v. That was another one unique to logarithms. And then the natural log of u over v is ln of u minus the ln of v, the quotient rule for logarithms. And of course, this works for not just the natural log, this works for log base, whatever, too, right? For all logarithms. So I'm going to use that here. I've got the natural log of all this stuff to the 1/2. So I'm going to put the 1/2 in front. And then I'm going to go 1/2, and I'm going to split this up, the natural log of the top minus natural log of the bottom. And then I have the product rule here. So I have natural log of the sine of theta plus the natural log of the cosine theta. And then minus, and I'm going to go natural log of 1 plus natural log of the, oh, I'm sorry, that's not u times, I'm sorry, I can't do that. I have 1 minus. I was thinking I had to multiply. I can't do that. That's not being multiplied, so leave that alone. And go ahead and take your 1/2 through. So I've got y equals 1/2 ln of the sine of theta plus 1/2 ln of the cosine theta minus 1/2 ln of 1 minus 4 ln of theta. All right, so I've used all the properties, and this is much easier now to take the derivative, right? So I take the derivative, y prime equals, and so I've got 1/2 stays there. Natural log of whatever is 1 over that whatever. But chain rule, derivative of sine, cosine, plus 1/2. Natural log of cosine, so 1 over, take that derivative, 1 over cosine. Take the derivative of the cosine, negative sine, minus 1/2. 1 over that, 1 minus 4 ln of theta. And now I'm taking the derivative of 1 minus 4 ln of theta. That's 0 minus 4. Derivative of the natural log is 1 over theta. So I got negative 4 over theta right there. Okay. And so I got to clean this up. Let me get a little room here. Clean this. Let me take this up here. So I got y prime equals, and notice right here I got cosine over sine. So I have 1/2 cotangent, and then I got 1/2 times, and it's negative sine over cosine. So that's negative tangent, so minus 1/2 tangent, or plus 1/2 times negative tangent, which again makes the negative go out front there, negative 1/2 tangent. And then I've got this mess here. I got, let's see, let me clean this up. I got minus 1/2. I've got 1 over 1 minus 4 ln of theta. And then I've got this negative 4 over theta. Times negative 4 over theta. So notice that leaves me with a negative 2. So I got, in the numerator, I got negative 1 times negative 2. I got a positive 2. Positive 2 over theta, 1 minus 4 ln of theta. And there it is. Again, I'd use these logarithmic properties. So let's rewrite this as the natural log of that minus the natural log of the bottom here. Right? So use that ln of u over v is ln of u minus the ln of v. And then I would go ahead and take the derivative at this point. So the derivative is 1 over that, but I got to take the derivative of 1 plus e to the x. Well, derivative of 1 plus e to the x is 1, or 0, sorry, derivative of 1 is 0 plus ln of e times e to the x. So it's just an e to the x there. Minus, now let's take the derivative of the natural log of 1. So that'd be 1 over that 1 minus e to the x. Take its derivative, 0 minus ln e to the x. Well, the ln of e, of course, is 1. So I just got e to the x over 1 plus e to the x minus, and over here I've got a negative e to the x over 1 minus e to the x. And so I just get a common denominator on this. Give this a 1 minus e to the x. Give this one a 1 plus e to the x. So the e to the x, 1 minus e to the x, negative times a negative is positive. This is all over a common denominator. Then I go ahead and distribute that, and come up here. So y prime equals e to the x times 1 is e to the x minus e to the x times e to the x. So e to the x times e to the x is e to the x plus x, e to the 2x, right? So minus e to the 2x plus, now I'm distributing this one here, e to the x through, so e to the x plus e to the 2x. Notice that one and that one are gone. So I've just got e to the x plus another e to the x. There's 2 of those e to the x's. Logarithmic differentiation is nice. This is usually done to apply the power rule, so to kind of release a variable from the exponential position, or maybe break up a product or a quotient. So this is an example of that approach. Let me go ahead and write this first in exponential notation. So all of this is to the 1/3, right? If a times b is to the 1/3, then a is to the 1/3, b is to the 1/3. So I could write this as x to the 1/3, x minus 4 to the 1/3, right? So I'm going to go ahead and write it that way, and then I'm going to, so logarithm, this is what sets apart the logarithmic differentiation. I'm going to take the natural log on both sides. So I run the natural log, and I run the natural log. And so I have the natural log of y equals the natural log of, and I can use my product rule to break this up. Oh, that's supposed to be a 1/3 plus natural log x minus 4 to the 1/3, right? And then I can use the power rule. Let me put those in front. So here I am in a much nicer form, arguably, to take the derivative. And so now we can take the derivative. All right, so we'll go ahead and run d dx on both sides. Let's take the derivative here. So we took the natural log, we applied the properties. Now we're taking the derivative. So the derivative of the natural log of y, I've got 1 over y, but chain rule, right? The variables do not agree. So I got to remember to put on y prime or dy dx equals. Over here, the variables do agree, so no problem here taking the derivative. 1/3 stays there. Derivative of the natural log is just 1 over x. One constant stays there. 1 over that x minus 4. Chain rule, derivative of x minus 4 is just 1. And now what I do is I'm going to go ahead and I got to solve for dy dx, right? I want to solve for y prime. So let's go ahead and multiply this side by y and this whole side by y. And so we got dy dx equals that awkward y right there. And then 1 over 3x plus 1 over 3x minus 4. So what do you do with the y? Well, go back to what y was. Y was given to us right here. It's the third root of x minus 4. We're going to go ahead and substitute that in. So dy dx, or y prime, is y times 1 over 3x plus 1 over 3x minus 4. And we're all done. There's y prime. Similarly here, I'm going to go ahead and take this original, here's my y, here's my x minus 2 to the x plus 1. And if I go ahead and take the natural log, then I can apply the power rule and put that in front. So I'll have the natural log of y, I'll have x plus 1 is being multiplied by the natural log of x minus 2. Okay? And then I can go ahead and take the derivative of that at this point. So dx, let's take the derivative. Let's take the derivative of this. All right, and I'm thinking this is a product rule. I'm going to have to use the product rule here. So the derivative of the natural log of y, 1 over y. Chain rule, dy dx. I'm going to write that as y prime. There's my dy dx right there. Times. Okay, derivative of the first. Derivative of x plus 1 is 1. Derivative of the first times the second plus the first. Derivative of the natural log is 1 over that x minus 2. Chain rule, derivative of x minus 2 is just a 1. So it looks like we have, and I'm going to go ahead and take my y to the other side. So I have y times all this. Looks like I have y prime, dy dx is y. Times the natural log of x minus 2 plus x minus 1 over x minus 2. And don't forget, you got to substitute that y in. This is what y is. So y prime ends up being x minus 2 to the x plus 1 times natural log x minus 2 plus x minus 1 over x minus 2. Or x, oh gosh, that's x plus 1. Sorry, that's a x plus 1. There you go. X plus 1, fix that. There we go. Let's go take the natural log of both sides here. I'm going to write this as secant to the third theta to the 1/2. So let me just write that as secant theta to the 3/2, right? Square root is to the 1/2. So we have the natural log of that, right? And then I'm going to go ahead and keep rewriting that with my properties. So that'll be natural log of y. Let me expand this. Natural log of theta sine theta minus natural log of the secant of theta to the 3/2. And then I have a product here, so I could write that as the natural log of theta plus the natural log of the sine of theta from my ln of u times v is ln of u plus the ln of v minus, I'm going to write that, I'm going to use the 3/2, I'm going to use that power rule, natural log of the secant of theta. Let's go ahead and take this derivative now. So I got 1 over y dy d theta. Natural log of theta is 1 over theta plus 1 over that sine. Derivative of sine, though, is the cosine. Minus 3 halves 1 over secant. Derivative of secant is secant tangent. And notice the secants cancel. And I'm going to take this y to the other side, y to the other side. So I have, let me come up here, dy d theta is y. So let's substitute y in. Here's my y, the original y, times 1 over theta plus cosine over sine is cotangent of theta minus 3 halves tangent. All right, the derivative of a to the x, as we've mentioned, is the natural log of a times a to the x, right? Natural log of a times a to the x, which is why, you know, when we had the derivative of e to the x, it just followed this rule. It's the ln of e to the x. Well, the ln of e is 1. So the natural log derivative of e to the x, of course, is ended up being e to the x, right? We're going to do it for all cases, so it'll also give us the key to finding the derivative of log base a of x. So log base a of x, if you remember your change of base formulas, you could write that as the natural log of x over the natural log of a, which let me write that another way. That's 1 over ln of a. That's your constant part times the ln of x. So when you run the derivative, the constant stays there, but then you run the derivative of the natural log, which is 1 over x. Okay, so the derivative of log, I just proved that the derivative of log base a of x is 1 over ln of a times 1 over x. And let's use those two rules. Let's do this first one. So here we're using the a to the x is ln of a to the x. Let's use that one here. So this dy dx is ln of 8 to the x squared, but we don't just have an x up there, we have x squared up there, so don't forget to take chain rule on that. Derivative of x squared is 2x, right? And so just rewrite that as 2x natural log of 8 and 8 to the x squared. And that's your dy dx there. Let's do it with a product rule here. So y prime would be derivative of the first times the second plus the first derivative of the second. So now we got ln of 6, 6 to that, and then derivative of negative 2x, negative 2. So I got 6 to the negative 2x plus, let's see, I got minus, what is that, minus 2x ln of 6, 6 to the negative 2x. Let's go ahead and take a 6 to the negative 2x out. So I'd have 1 minus 2x ln of 6. That would be our derivative there. Here, so we got a log base 4. So we're going to go ahead and use that rule that the derivative of log base a of x is 1 over ln of a times 1 over x. All right, so we'll use that rule here. So that dy dx ends up being 1 over the natural log of 4. Notice my a is 4. There's 1 over ln of 4. And then we got 1 over that stuff in the inside, right? 2 plus x ln of 4. Now, it's not just x right there, so I got to go ahead and take the chain rule. Derivative of 2 is 0 plus, the ln of 4 is actually the constant here, and then derivative of x. So 0 plus 4 ln of 1. And so this just ends up being ln of 4 over ln of 4 times 2 plus x ln of 4. Well, the ln of 4's cancel for us, and we got 1 over 2 plus x ln of 4, and that's our derivative here. This one I would go ahead and rewrite this with my, it's a logarithm, but I would go ahead and rewrite it before I did this with my rule. So I have log base 3 of that x squared x minus 1 minus log base 3 of 2, right? Or you get, actually I'm going to change my mind. Let me rewrite that, sorry. Let me write it this way. That's log base 3. I have a half times x minus 1 to the 1/2. There you go. So everything's just being multiplied there. So let's go ahead and rewrite that as log base 3 of a half plus log base 3 of x plus log base 3 of x minus 1 to the 1/2. We're going to go ahead and use the power rule of logs to rewrite that one before we take this derivative. Now let's go ahead and take the derivative. So dy dx, derivative constant 0, plus derivative of log base 3 of x is just 1 over ln of a times 1 over x, right? It is just an x right there. Plus 1/2 stays there, 1 over the ln of the 3, 1 over the x minus 1, derivative of x minus 1 is just 1. So it looks like we got dy dx ended up being 1 over x ln of 3 plus 1 over 2 ln of 3 x minus 1. And let's say we want to get a common denominator here. They both have an ln of 3. The one on the left has an x. I need to give this one an x. So now they have an x and a x ln of 3. This one needs a 2. Now they both have 2x ln of 3. And the one on the right has an x minus 1. So I better give this one an x minus 1. And then I'm going to go ahead and distribute that too. I got 2x minus 2 plus x over 2x ln of 3. X minus 1 is our common denominator. Two x plus x, I got 3x. Get the minus 2, 2x ln of 3, x minus 1. Notice there's no base on this log, so this is the common logarithm. It is a base 10, but let's go ahead and rewrite this before we even do it with the power rule. So we got y equals, I'm going to put that ln of 10 in front of all this, and then I'll have log of this stuff. Sine secant e to the x 3 to the x. And then I'm going to expand that. So I have ln of 10. I have log of the top, sine secant, minus log of the bottom, e to the x times 3 to the x. Then I'll use my quotient rule. So product rule, sorry, log of sine plus log of the secant, and then minus, and then I'm going to expand these, log of e to the x plus log of 3 to the x. Notice that that minus will apply to both of those there. So that's going to be minus log e to the x minus log base 3 of x. So here's what we got. Y equals ln log of sine log secant minus log v to the x minus log 3 to the x. Hey, let's go ahead and finally take the derivative. So y prime dy dx would be oh gosh, that's had a 10 on that. You know what? Let me take the ln of 10 through first. Sorry. Let me take that through before we. So I have ln of 10 log of the sine plus ln of 10 log of the secant minus ln of 10 log e to the x minus ln of 10 log 3 to the x. Okay, so I got a number in front of these. Now when I take this derivative, number stays there. Derivative of the log base 10. 1 over ln of 10. Remember, it's log base a, log base 10 here. 1 over ln of 10. 1 over the sine. Derivative of the sine, cosine. Plus the next one. Ln of 10 stays there. 1 over ln of a. In this case, it's 10. 1 over secant. Derivative of the secant. Secant tangent. Minus ln of 10. 1 over ln of 10, 1 over e to the x, derivative of e to the x, ln of e, e to the x. I'm not going to write the ln of e because it's just 1. Minus, last one, ln of 10, 1 over ln of 10, 1 over 3 to the x, and I'm running out of room here, ln of 3 and a 3 to the x because I took the derivative of 3 to the x there. Let's see if I can't fit this in here. Notice my ln of 10s all cancel on these. And so I've got cosine over sine, so I got cotangent of x. Plus, here I've got the secants canceling. So I've just got tangent of x there. On this next one, I've got my e to the x's are canceling, so I'm just left with minus 1 right there. And then on this last one, I got my 3 to the x's are canceling. So I've just got minus ln of 3 left. And there it is, kind of cleaned up pretty nicely on that one. I'm going to rewrite this. Let me leave my theta here. I'm going to use the power rule and put that in front. So I've got cosine ln of 2 in front of this log base 2 now of e. Okay. And then what I'm actually going to do on this is I'm going to use my change of base formula. So I got theta, cosine of theta, and that's just because I see this ln of 2. So let's use our change of base formula and change that log base 2 of e to ln of e over the ln of 2 and see how those ln of 2's cancel. That's really nice. And we know the natural log of e to the 1. We know this is just 1, right? So I actually end up with just theta cosine theta, which is nice. Now I can just run product rule. So the derivative, or I'll do it dy d theta this time. Derivative of the first times the second, plus the first, derivative of the second. And so dy d theta ends up just being cosine theta minus theta sine theta. And that kind of cleaned up real nice for us as well now. Thanks so much for watching. I know that's a pretty long section. See you next time.